我先照你那个思路对，对，
Silly question.
There was a paper just recently came out. Nadia was on it. I could get a CD fit in, and yeah, so 100% of the optical length.
Hi everyone.
From the center to our circle.
Yeah.
And
I sent a message on one of the
Like see
with a link to
central.
a Google Drive on which you can download basically all the material and also install things. So while I'm connecting to them, maybe you can download the things and make it work. It should work. In the notebook, the three first cells tells you what environment to install, because you need like Python 3.11 or like an old version to work. So please try to follow the instruction, because otherwise you will be the package and all that.
install.
Did you get my email?
Yes, I am installing Zoom. Sorry, Zoom. So anyway, the first cells you can check on the notebook after installing all the packages and all. You can look at the event file. So basically a picture taken by it was by Chandra by using the DS9 command. So you can do DS9 and the name of the event file, which is given here in the practice part. Have it. In the meantime, I will try to.
You're not sharing.
My Zoom is not.
Okay. You can try to log in on the website instead of the app. Thank you.
Anyway, with the image, you can explore and eventually find like a source that look interesting to you by just zooming and yeah, exploring. You know? And then with that, you can create like a region, a circular region around it, and for which we can extract its source.
But free to set up list.
Using just this, not wrong.
The internet is really slow. I'll go grab it, don't worry.
Thank you.
Just needed your presence.
See it here as well, right?
Okay. So we go in the tutorial thing, we do DS9.
Oh, we have USB-C. Oh, thank you. Just
So it was supposed to be interactive, but it's not. 9 data. Did you arrive to the DS9 thing? You have this image. If you go in scale, you can put it in log scale because it's better to see points. You change the. So here you can see like few sources. So if we do a little zooming, this one for example. Zoom. So here there's a small source. If we go in the edit region, we can add a circular region and then save it by going to region. You can also modify the color, the width, the properties and everything. And you can also save it. Source region, and so now you have like a region file, and you can also do this for the background because when you do spectral fitting, you need the source but also the background around it to know what is the normal noise in that region. So for that you go in region you use a shape thing and you go to Analysis. You have one, and you can put it around the source. So the central region will be excluded, but not the upper region. So all these Analysis will be the background region, and that will be useful for the template fitting. You can save it. We need to remove this one back. This is really like a tutorial just to appreciate how things works. Play around with it, but in normal life, you will have a catalog of sources or apply like some methods to detect the sources, which will not be covered here. Anyway, now that you have the background, you can save it. So,
Any recommendation on size for this background extraction?
in my code, I fix it to 20 arc seconds around the source region. So, yeah, a bit outside of it.
Can you just, I don't know about the data set here. Can you just explain what the data set is?
Oh, sorry, this is just an observation by Chandra.
Okay.
This is in Cosmos.
Mhm.
And if you can get those by just
I haven't downloaded it. Yeah, I didn't download it because it was too big.
yeah,
so-
no worries.
But I just wanted to like have you.
So
say
there's
it.
just if you know in which observation it is, you just do command line, which is I don't know where it is, but basically it's Chandra.ID,
Okay.
and you put the number and you have all the information about it, including the event file, and then you go on this. And you can play with it a bit, but
So this is an AGN, like in the Cosmos field.
let's say yes.
Yeah.
Like I don't know this particular source, I just picked it because it was there and I cannot move.
Is it possible to smooth the image on the fly in DS9 or no?
Smooth image, what do you mean, like change the scale?
Smooth.
Yeah, analysis smooth. You can smooth it. You can also,
Okay.
and there's like a block with these.
Look more.
Better than me.
Great.
Then you can save the background. BPG. After that, you can extract the spectrum. And for that, you need to use the Sherpa package and follow this instruction. So you have the input files, which is the event file, which is event here, and you tell the function in which region to extract. So that is this region, source region, the one you saved earlier. So you can put it with any source. Then you have the output, then the background file, so the analysis around it. And also here, for example, the energy range that you are interested in. So you can put like 310,000 electron volts. And this will provide you this will give you spectrum. It's because of the spaces. Nothing goes very well, I'm sorry. But yeah, you just can run it upon yourself and you will have extracted the spectrum. showing you normally it works. And yeah, you can practice with any source. And in the data that I sent, there are two observations. And two observations that are overlapping. So there are some sources which are in common with the two observations, and therefore you can extract the same source in two observations, then combine the spectra together. And for that, you need to run the script called script.py, because it does not work in the Jupyter notebook. So you cannot, even if there are Python commands, you cannot run them. So basically just go on, this should work. Script.py. Take a bit of time, but basically, if you want to, we can have a look at what's inside this code. Yeah. Yeah, sorry, before running it, you need to do change the path here and put it the one that are created in your environment. Because otherwise it will run forever. If you just modify this, is in laptop. It should work, hopefully. Basically, what it does, it does the same thing as what you were doing before. So create like a region, extract it, but automatize. So yeah, there's a table in which there is the era and deck of the source. There's also the source radius. That is one of the output of the source detection. And then from that, it creates the source region file and the background region files. Save them somewhere, and then extract it with the space extract command, as I tried to show before, but normally it should work. And then to combine them, there's basically just one command, which is combine spectra, and you just put them all one after the other. Okay, so it worked. So here in ls extract a spectra, there is the spectra extracted in this observation in the 2023 and also in the 2024. And you combine both of them and you get the combined SCR CIF pipeline. So that is how to do it. So if you want to do it by yourself later on, you can just have a look at this script.py file and reproduce the steps.
I have a maybe basic question, but this code or these functions are especially to work with Chandra data, or I can use it to.
I think they've been designed with Chandra, but they might work with others. I am not sure. Mostly with Chandra, and the Chow package is designed by Chandra. Maybe because it's X-ray, it should so work, but maybe not as efficiently. But yeah, maybe I should have precised the tutorial is for Chandra X-ray.
So another quick question. So you're basically combining here spectra taken on different dates, is that right?
Yes, two different observations. There are no Cosmos, they take some different overlapping observations.
Yeah.
And so this source is present in both.
So if you go on the archive, and let's say you have observations that are overlapping but on different dates, is it better to combine them after you extract the spectra? Or is it better to actually combine the event files into like one?
I'm not fully sure of. Might that be actually the same because they are. You just extract the photons in both observations. So it could work exactly the same, but I'm not fully sure of if there's actually a difference or not.
Thanks.
The method I'm using. And also here you have to register the galaxy extinction from the Milky Way, given the coordinates of the source. So this package is called GD by C. That given the coordinates give you the galactic NH, which will be useful later on to spectral fitting. Then to visualize the spectrum, you have to change the path as well. And then you load the combined file, the combined spectrum, and that looks like this. So it's not that pretty, but there are many functions to make it a bit better, notably this one, which is probably the one I'm most often using, which is grouped by signal to noise. So basically it sums all the bins until you get the minimum signal to noise, and you obtain this spectrum. It's not great, but it is the average, I would say. So now that you have your spectrum, you
Sorry,
can.
I have another question. This Chow or whatever, do they, because Cosmos is a crowded field, it is possible that in your background you actually have another agent, or it's not that crowded?
It's possible. Okay, in my code, normally I have a function that checked if there are other sources nearby and you can remove it. So in the background file, you can do minus circular region. So if you have the coordinates of another source, you put it and you remove it from and that works. That's a good point, but here I checked. So for the spectral fitting, you need to load many packages. Notably, for fitting, I'm using the UX Clumpy model, which has been developed by MS. And the algorithm is called BXA, also developed by MS. And basically here we're gonna use that to fit the spectrum that you extracted just now. So for that, the first step is to set up the solar abundances and some section table. So yeah, some physical parameters. It works. Then load the model, which is just the table. On the light eventually.
Switch on the light.
So here in this case, we load like one specific model, but there are many other models. So from expect, Sherpa have all the expect models. So just if you just want to fit like a power law and absolute power law, you can. But here we decided to go for a more fancy model. So basically, motivated model, which is also clumpy and have different parameters. Then you have to load the combined spectrum, which we do here. And also you have to set up the statistics in the CStat because otherwise it might be not mathematically rigorous to do to fit because you have to fit simultaneously the background and the source, and if you don't have C-stats, it's not good. So now that you have loaded the thing, you have to set up the parameters of the model. So you create some parameters. So for example, here there's one called CRC level, which is the normalization of the torus component. You fix the minimum value, the maximum value, and the initial value. And in this case, because it's linear, and usually I prefer to work with logarithmic parameters. So I just link this parameter to the parameters of the torus. So the normalization of the torus is 10 power this one. You can do the same with NH, which usually goes from 20 to 26. NH is the obscuration of the torus. And also you can link it as well to the torus parameter. There's also the soft scattering component. You know, when you fit a torus in the X-ray, there's often like a soft scattering component that you need to add. It is kind of mirroring an absorbed emission, and but it's softer, so its normalization is much lower than the normalization of the initial torus model. So it's you can only see it when the torus is strongly absorbed, basically. Then you link all the parameters together, the photo index, the inclination, the opening of the torus, the covering, basically all the parameters of the model. And here you have the model with all the different parameters, the ones that are frozen or not. And yeah, so that's the initial step. You can later on create the priors. So DXA is fully Bayesian algorithm, and use some priors. So if you know that, for example, the gamma, the photo index of the power law, there are some values which are given like it's not it's more like a Gaussian prior. You can fix a Gaussian prior, for example, on the photo index, and you fix it to the value which is here, and with some scattering. While from others, you can prepare like a uniform prior. You have no idea of what is the normalization, so you let it vary uniformly between whatever value. But if for some reason, for example, you have the mid-infrared information on what is the 6 micron luminosity, and you use the 6 micron to the 2 to 10 kV luminosity, you can create like a bridge and between mid-infrared and X-ray, and you can guide basically the opposite of what Carolina showed earlier. You can do this in the X-ray. And after that, there are other parameters. So for example, the inclination, but in this case, we fix them because often you don't have enough counts to have like a good fit. So you prefer all these parameters will be degenerate. So it's better to fix them to the value rather than let them free and basically lose some time and some energy for nothing because you cannot constrain them. So now you have the torus, and one last component is the redshift. So you create the parameter and let it free to vary between 1 and 0 and 6. And in this case, this source is a spectroscopic source. So the redshift is known. So you do not let it as a free parameter. So you go in. Basically, you fix the value of the redshift parameter to once the value that you found, and you don't add the free parameter in the fit. But we'll see later that we can actually with BXA incorporate like a full photometric redshift posterior as a prior for the redshift. Then you have the galactic absorption. And so for that, you will read the file that you saved earlier. And the galactic absorption. And then you need to feed the background of the source, the one you extracted. There's a function called auto background, which is a PCA algorithm that will find basically try to fit as best as possible, at least find how many parameters are necessary to fit the background. And then either you fix the parameter to the normalization because you want to make it faster, or you let it free to vary as you want. In this case, we freeze the background.
How much impact has the background modeling in the results?
Not really sure. It has some impact, but not so much. Then you create the prior function. So from the list of priors that you created before, you transform them a bit differently in such a way that the algorithm knows how it works. You create the folder in which you're gonna save the fit. Then you have the parameters of the fitting algorithm, so the number of live points, and the frac remains. So the fraction, basically the threshold at which the fit will say, oh, it's good enough. If we want, we can go to see this animation on how BXA works. So we have the number of points, which are the live points, and they are randomly distributed, and as a function of where they are, they obtain a different value and a different likelihood. And the one with the less likelihood is removed and put back to randomly inside the other region, and little by little it gets closer to the wrong truth. So basically that's what it does, but constrain the parameter space in this way. And up until basically everything which is outside is irrelevant. And then you can just run the fit. Now that you have fixed all the parameters, you have set up everything, you can just run EXA. You will see that, for example, here's the normalization of the torus, here's the photo index, here's the obscuration, and little by little. The soft scattering normalization usually is kind of irrelevant. You don't need it that much, so most of the time it will not be constrained. 5% of it. See, the normalization is good, the photo index is within this range, and the obscuration is quite well constrained as well. So now that you have hit all the initial parameters, you also want some additional parameters. For example, for example, you have the normalization, but what we care about in reality is the extra luminosity, not just the normalization of a random model. So for that, you have to, what do? You use the full posterior distribution, because you have the full posterior distribution of the source. And for each source, you will compute from the model, you will compute with this function, calc energy class. from 2 to 10, and that will compute basically the flux in that range. Then you compute the distance at this given redshift, and basically is the absolute flux, but then also yeah, because sorry, there's the unabsorbed flux, and anyway, so to get the X-ray luminosity, you measure the flux in the 2 divided by 1 plus redshift to 10 divided by 1 plus redshift with the AGN model. Also, we found there's like an offset between X clumpy and just a regular power law, so we have to just multiply by 0 point this value, and that will give you the flux. And then you do the flux time extent square and 4 pi, and that will give you the X-ray luminosity. If you do this, basically now you have the full thing. And now you can have a look at the posterior distribution and see how it looks. So for example, here you have the X-ray luminosity, which is fixed, which is well constrained at 44.6. You have the obscuration, which is not fully constrained, but at least we know that the source is an obscure because it's 20 to 22. So it's a broad obscuration distribution, but at least it's not obscure. It's quite good. Just to say it's not obscure. You have the flux, the gamma. BXA also automatically plots some plots. So with IPython display, which partly does not work with Chrome, you can just this is some plots which are automatically created by BXA, and you can look at the degeneracy between some parameters. For example, the normalization and the photo index are kind of correlated, because if you increase the photo index, you can also if you increase one, you have to increase the other, and you kind of compensate the this one is kind of representative of what happened and how all the different life points progressively where they lived in the parameter space. You see that at some point it gets well constrained at some point. I don't know what it is. Then you can plot the best fit. If I have time to go in the details, or I should just research. Okay. Basically, now that we have all the posterior distribution of all the parameters, for each of them you can create the spectrum of it, and then all the spectrum you can combine them and get the medium spectrum of these sources. It's a bit slow, but work. So yeah, basically what it does, it loops through all the parameters and gets the median value of the torus, of the scatter component, of the background, and of them. Yeah, it's my code, so it's not that pretty, but it works. And if you want, you can have a look through it, and if you don't understand, you can message me, and I will try to explain you the best I can. So the plot looks like this. So now you have the blue dots are the data points. The red curve is the best fit model. Here you have the background model. And in yellow is the scattering component. So as you can see, it's kind of useless for this source. Yeah, so that's the first example. So it was just a random source that happened to be in those two observations. I did not take it for any specific reason. But if you see in the data folder, there's another source called 212. And this one happens to be obscured and has a lot of counts. So, and it's already combined, so you can just load it and feed it again. So, and this source, on the other hand, does not have a spectroscopic redshift. So in this case, we will add the prior of the redshift, which is not the case here. Here we just repeat what we did before. So the priors for all the different components. So the normalization, the photo index, the obscuration, and the soft scattering. But in this case, as I said, we don't have the spectroscopic redshift. So we'll go in this direction, and you will interpolate the cumulative distribution, and from that you have a prior that will be used later on in DXA. The source is at 240. Then again, the galactic absorption, the background again. So it's just things you've seen before. Then you create so then you create the folder in which things will be done, and then you can run again BXA with the same parameters of the algorithm. So the same number of light points, the same remaining fraction. So yeah, once you have the recipe, you can apply it to any source. And depending on what you want, you can fine tune, and if you have a lot of counts, you can add more free parameters. But if you have 30 counts, you just do what you can. So just fit a power law with an absorption is enough. But yeah, we saw this morning there's like the inclination of you can even get the inclination of the disk, but it's not possible with this model. Yeah, many different things can be done, but yeah, but because there are more points, it's slower. Some points will be done, so we can run it as well. But then it would just be plotting things. So if you have any questions on how things work while it's reading, tell me.
The posterior distribution of the X-ray luminosity of the second source. Oh, we know which.
Okay, so actually this was one of my concern in my first paper in the PhD. I actually used the prior on as I said before, like if you get the 6 micron from the LCD fitting, the 6 micron luminosity, you can constrain the X-ray luminosity, and therefore kind of help to the algorithm to decide which of this double peak is the best solution. Did not even notice there was a double peak. Yeah, that can be really useful, but it's more time, and also you need to trust the LCD fitting, and as we saw earlier, there's a lot of parameter degeneracy, so you know what.
That's a very nice question. So, how do I know if X-ray source is 80?
If it's in the X-ray, it's most likely to be an AGN.
But would it be like galaxy cluster? You
The
have to do
s-
like morphological selection.
The size will be, it will not be point-like. Most likely, processor is much larger, and I think as well the shape of the spectrum is totally different from it's not a power law. Don't remember the galaxy cluster person, but it's different. The shape of
And it'll be like in Chandra, it would be much more diffuse.
Yeah,
Like,
exactly.
I mean,
And technically, I think you can fit it as well, but you just need, instead of using a torus model, you use whatever model is
Yeah.
used for clock.
yeah. APAC or something, or Nicole. Is this applicable? I mean, somebody asked this already. I can throw in them. I mean, Rosita. Something similar, you know, this be adapted for Erosita?
Yeah, actually, at some point I used a bit on the data on IFETs, and that works as well, but the range is much smaller, so you just have 0.5 to
Oh,
yeah,
the range is much
the
smaller.
energy range in which much smaller. So
Mhm.
for obscured AGN, they will decrease rapidly, so
Mhm.
it's much more complicated.
I mean,
But it is useful, and
is this like fun, you know, does the CD fitting work as well for Erosita, or do you have to add like, is there different templates? Yeah.
CD or
Right. The X-ray, I mean, sorry, the X-ray, yeah, I shouldn't say SED. Yeah, yeah, the X-ray spectrum, does it fit just the same way, or do you need other files?
It fits the same ways, but maybe some models might be more adapted to Erosita data for maybe more details on this specific region, this energy range. But it works as well. Yeah, again, like you have to choose the models as a function of what you have and what you want. This only comes with kind of experience and people that work with you.
Yeah.
This was takes a lot of time. 1 point. Well, yeah, now you're, well, it's the previous time I run the code. Yes, there's this double pick. At the same time, both of them is quite narrow. The double pick is between 2 decks, so 0.2 decks, so it's quite all right. But sometimes you will see, because it's the full person, you explore the full parameter space at the same time, you might have one pick at 44 and one pick at 45 or 46. In that case, it's much more problematic to have 2 picks.
Is NH the galactic absorption or the?
No, this is the
tourist
total line of sight obscuration. So technically, we don't know if it comes from torus or from. Well, in this model, we assume it comes from torus.
Yeah, it's much greater. I mean, that value is much higher.
But in reality, it could also be from the galaxy.
Yeah,
The galaxy itself is very dense, or
but this is,
But
this
this one-
number that corresponds to the torus.
yeah, no, it's in the modeling, we assume it's come from the torus. So yeah, that should be the fit what we obtain at the end. That's it. So I was even thinking of other sources with a lot of counts, and some of them is one of them is content thick, but I don't know if we have time for that. So maybe I can just put it on the slide for people to buy or. Thank you for.